Let's look at the basic integration formulae. Here we have 22 formulae. Maybe in some other book you can find 19 formulae, 18 formulae, 20 or 21 formulae, anyway around 20. But let's talk about integration techniques that we have to use besides of this formulae. Let's study the substitution method. If our integral can be recognized as the following function, so we can see the u to the power of n and the derivative of u, which is du over dx, then we can express this integral as u to the power of n du. And in this case we already know that our integral will be equal to u to the power of n plus 1 over n plus 1 plus c. And here we have this notation. We have written du over dx times dx as du. Let's look at the example. We need to find the integral of this function. We can see that our 3x squared plus 1 is actually the derivative of x cubed plus x, right? So we set our u equals x cubed plus x, and then our du will be equal to du over dx times dx equals 3x squared plus 1 times dx. And by this substitution we will have this integral u to the power of 5, where u again is equal to x cubed plus x. Then we can integrate according to our formula, and this will be u to the power of 6 over 6 plus c. And then we can substitute back our x for our u, and finally we will have x cubed plus x to the power of 6 over 6 plus c. Let's look at the following example. We have integral of log with the base 2 of x over x dx, and let's just separate our constant, which is ln2, using the logarithmic rule. So we have 1 over ln2 multiplied by the integral ln x over x dx. And here again we can recognize our u equals ln x, and our du will be equal to 1 over x dx. And we have this integral 1 over ln2 times integral u du. And we know that in this case this u du will be equal to u squared over 2. And if we substitute our x, finally we will have this ln x squared over 2 ln2 plus c. Our next integration technique is integration by parts. If we have this integral of u dv, and if we can very easily to calculate the integral of v du, we can use this formula. Let's look at the example. We need to find this integral of x cosine x dx. We use this formula and we denote our u as x. It means our du will be equal to dx. Our dv equals cosine x dx. Our v equals sine x. And this was chosen because we have simplest antiderivative of cosine x. And then our integral will be equal to the following: x times sine x according to our formula minus the integral of v du, which is sine x times dx, and this will be equal to x sine x plus cos x. And don't forget about c plus c. Let's look at the next example. On integration by parts, we need to find the integral of ln x. So since this integral ln x dx can be written as this ln x times 1 times dx, we use this formula u dv equals uv minus integral v du. Our u will be equal to ln x, so this simplifies when differentiated. Our du will be equal to 1 over x dx. Our dv will be equal to dx, then this is easy to integrate, and our v will be just x as simplest antiderivative. And finally, our integral according to our formula will be equal to x times ln x minus the integral v du, which is x times 1 over x dx. And finally, we have this x ln x minus integral of dx, which is x ln x minus x plus c. Our next integration technique, when we want to integrate our rational functions represented as rational fraction. Let's look at this example. We need to integrate this 5x minus 3 over x plus 1 times x minus 3, which is the same as 5x minus 3, x squared minus 2x minus 3. And we know that this fraction can be represented as the sum of the following smaller fractions: a over x plus 1 plus b over x minus 3. So our task is to find this a and b. If we take our common denominator, we can find that this 5x minus 3 is equal to a times x minus 3 plus b times x plus 1, which is equal to a plus b times x minus 3a plus b. So we get the corresponding coefficients at x and just this minus 3a plus b. So from this we can obtain these simultaneous equations, and we can find our a equals 2 and our b equals 3. So finally we can rewrite this fraction as the following: 2 over x plus 1 plus 3 over x minus 3. And then we can integrate these fractions separately. So our integral will be equal to this integral, 2 over x plus 1 plus this integral, 3 over x minus 3. And finally, according to our formulas, our integral will be equal to this 2 ln of modulus x plus 1 plus 3 ln of modulus x minus 3, and we don't forget about c. For more general case of integration of rational functions represented by rational fractions, we will use this method. First step: let x minus r be a linear factor of g of x. Suppose that x minus r to the power of m is the highest power of x minus r that divides g of x. Then to this factor assign the sum of the m partial fractions: a first over x minus r plus a second over x minus r squared plus etc. plus a m's over x minus r to the power of m. And we need to do this for each distinct linear factor of g of x. Then our second step: we set the original fraction f of x over g of x equal to the sum of all these partial fractions. Clear the resulting equation of fractions and arrange the terms in decreasing powers of x. And the last step, we equate the coefficients of corresponding powers of x and solve the resulting equations for the undetermined coefficients. I hope you will enjoy the integration and integration techniques. Thank you for attention. Bye bye.